My dear student, colleagues, and all the viewers for watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. So, good afternoon to all. I'm 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 going to welcome you in our international webinar, and this is our 95th international physics webinar. So, uh, today we are going to bring a famous laser physicist and in the world, and I'm happy to share with you all that he has already connected with us. So I would like to welcome our speaker. So good afternoon, sir, and it's our pleasure and honor to host you in our international physics webinar. So for those who are new, I would like to introduce that we have divided our webinar into three parts. First, we'd like to uh, introduce our speaker with all of you, though many of you may know our speaker. And then we have a time where in that time our speaker will deliver his speech, and at the end we have a discussion time. So I think you have already come to know the title of our today's speaker, and title is The Extreme Light. And our speaker is Dr. G. Ravindra Kumar, sir, Senior Professor, Department of Nuclear and Atomic Physics, Tata Institute of Fundamental Research, Mumbai, India. So if we see his academic and research background, we can see Professor G. Ravindra Kumar, famously known as the laser physicist of India, is well known for his research in plasma and optical physics, focusing on the ultra-short pulse and warm dense matter. He is a senior professor at the Tata Institute of Fundamental Research, Mumbai, where he has been instrumental in setting up ultra-short pulse high-intensity laser laboratory. The lab works in laser matter interaction, probing matter of extreme density and temperature. For his pioneering experimental contribution, he has been facilitated with the prestigious Shanti Swarup Bhatnagar Award 2003 and Infosys Prize 2015. In 2018, IIT Kanpur conferred upon him the prestigious Distinguished Alumnus Award for his academic excellence. Professor G. Ravindra Kumar sir obtained his Bachelor of Engineering honors in Mechanical Engineering and MSc in Physics in 1983 from the Birla Institute of Technology and Science, India. He then joined the PhD program in physics at IIT Kanpur and completed it in 1990. After a year-long postdoctoral work at the institute, he joined the Department of Atomic and Molecular Physics at TFR in the group now known as AFIL. Currently, he is a senior professor at TFR. Professor Kumar's research area primarily includes studies of interaction of intense ultra-short pulses of light with single molecules, studies on the behavior of short, dense plasmas created by intense femtosecond light pulses, and search for better nonlinear optical materials. At TFR, he has established a strong laboratory for studying the physics of hot dense matter produced by the ultra-short laser pulses. Some of his noteworthy findings include the first demonstration of ultra-short giant magnetic pulses in dense solid plasmas, enhancement of light coupling, and the hard X-ray emission from nanostructured surface. He was one of the principal investigators of the experiment done at TIFR in collaboration with Rutherford Appleton Labs UK, which highlighted that femtosecond laser pulses kicked electrons to speed faster than light within a glass target. Professor Kumar's research findings have significant implications for laboratory testing of astrophysical scenarios like supernova explosion and high-energy particle production. So Professor Kumar's work has won him numerous prestigious awards on winning the Infosys Prize in Physical Sciences in 2015. He said, experimental science needs a lot of motivation, a can-do spirit, and passion. It needs a tremendous amount of patience, and it needs the ability to interface with a lot of things. And the biggest thing is persistence. If you don't do good experiment science, there is a no good technology. He's also a fellow of Indian Academy of Sciences and Indian National Science Academy, member of the Optical Society of America, life member of the Indian Laser Association, Plasma Science Society of India, Indian Society of Atomic and Molecular Physics, and Indian Society for Mass Spectroscopy. He serves on the International Committee on Ultra High Intensity Laser of the International Union for Pure and Applied Physics. We can see his awards and honors. and his research gate ID, and his point is 40.67. So thanks all for all of your questions. Now it's time to go to our speaker. So thanks, sir, for accepting our invitation, and we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir. So the main aim of our program is to motivate and encourage our students in this corona pandemic situation, and we have successfully completed our 94th international physics webinar. And in those physics webinar, physicists from different countries are coming as a main speaker, and they're sharing their knowledge with our students. I think by this way, our students are benefited. So thanks again, sir. So it's your time, sir. You can start your session, sir.
Sure. Thanks, Pretam. And good afternoon, everyone. Kemonacho.
Hello.
And I hope, and thanks so much for giving me this opportunity. And I know, it's actually very unusual that we are talking on screens, but as Professor Das was saying, well, every bad thing has some good thing in it. So the pandemic has opened up these kind of channels. Otherwise, just imagine us talking on a Monday afternoon. You would have been busy with many other
Yeah.
things, and I would have also probably had some things, and I would have said, okay, some other time.
Yeah.
But luckily, we have got together, and I must tell you that Professor Das is an extremely persistent man. And just as I said, good experiments need a lot of persistence. So he tried his experiment with me, and he has been asking me for a long time. And I feel quite bad to say that, initially I just sort of postponed it. But then I had to say yes to him because of his enthusiasm, his motivation. I'm actually surprised, and I'm probably not so surprised given the motivation that I've seen, that he has carried this. You people have all carried it for 94. So I'm in the 90s, and as all of us in the subcontinent love cricket, so I'm in the 90s. So I asked him, you should have given me the chance to score the 100. But then I was humbled when I heard that the 100th talk would be by somebody who is extremely, who is at a much higher level of accomplishment. And I would like to look forward to, I would look forward to listen to that talk myself. So I'm sure, Pretam, you can send me the link
Yeah.
when
Yeah.
it
Of course,
comes.
sir. I'll definitely send the link, sir.
So, and I'm very pleased. And so, as a fellow South Asian, and in fact, Pritam was telling me that the idea of this is to say that people can do interesting things. Good or great is a matter of perception by lots of other people in the world. But you can do interesting things, and you can amuse yourself with some good stuff right in the subcontinent. You don't, many of us go abroad to do things in Western universities or in Japan or, various other advanced countries. But it's possible right in Bangladesh, I'm sure, in the next few years or so, while you grow up, to do some very interesting things, do some excellent work that satisfies you and also brings laurels to the country. So I'm very happy, and thanks, Preetham, once again. And now let me just start off. So I'm going to tell you something about extreme light, which in turn produces extreme states, right? Each of these needs a definition, which I will do. What do I mean by extreme in both in the case of light and in the case of matter? And the tabletop is something that that's the reason why I'm able to give the talk today. Traditionally, these studies have been confined to huge installations, big laboratories in the world, and enormous amount of money, right? Which I think smaller countries like ours cannot afford. But due to a very happy and fortunate development in the 1980s, the field has got somewhat democratized, and now we're able to do things right in Bombay. And I'm sure, depending on your interest, I'm sure you'll be able to do it right in your own university in the near future. So, what am I going to talk about? This picture itself has some things for those people who can see. The title is sort of the title is placed in the right hand rectangular box, and I am indicating a cone here. And I'm sure you'll appreciate what this means. There's this convergence of something here, or let me say focusing of something. So I'm going to focus on these things, and you will realize the value of the meaning of these words, focus and converging into a small spot, etc., in the next few minutes. We are at the ultra short pulse high intensity laser laboratory. The short form of that is Uphill. So people ask me, how did you choose this name? I said the name chose itself. We wanted to just call it high intensity laser lab, but an ultra short pulse because there are other pulses, other lasers which are long pulse lasers. And it turns out that nobody had chosen this name. So we sort of grabbed it and we made it our name. So if you're on Google, you type out Uphill, you'll actually come to our lab, right? So do visit the website. And Pretam and a colleague visited us 2 years ago, I think. And
Yes.
I would love to invite you all to visit when the time permits, when the conditions permit. And you're most welcome. And I'd be happy to show you around. So these are all my colleagues over the years, lots of students. In fact, our work is majorly driven by young people in their 20s. The professors are few, but the students are many. And so the main people, along with my colleague M. Krishnamurti, whose name appears here, I share this lab. And over the years, we have had several students, postdocs, and colleagues who have contributed to this. Our own ex-students, so for example, Rajiv now is at RAL UK, and Sandhu, the first one mentioned here, is a faculty member at the University of Arizona in the US. And several of these people are in the US or UK or elsewhere in Europe doing their postdocs or having permanent positions. On theory and simulation, we have had excellent collaboration with Professor Kao, Professor Das, and Professor Sen Gupta at the Institute of Plasma Research in Gandhinagar, about 500 kilometers from here, and also from the groups in UK at York and at Rutherford Appleton Labs, and in Celia Bordeaux in France, and also one colleague at CERN. And not to forget, several simulations for us done by Professor Zhengming Sheng and colleagues in China, right? So these are some of the pictures just to show you that the people are really young. So young people have a way of doing things which older people cannot. So I wish you, I'm sure all of you will do great stuff as you, mature in the university. And then these are more recent pictures of our lab. You can see a bit of this was taken right inside the lab. So you can see two different parts of the lab with lots of vacuum systems and optics and measurement devices and so on. And of course, very bright young people. So extreme light, right? So how do we define extreme light? Extreme light in one sense, in an accepted sense now, is actually something called it's a high energy ultra short pulsed laser, right? Light from a high energy ultra short pulse laser is what is called extreme light. Why is it extreme? We will see. Just one second. Yeah. So what is the meaning of what is extreme about this? The extreme parameter in this light, from this ultra short pulse high energy laser, it is what's called the peak power. So power, as we all know, is described as energy by time. So peak power, because everything is crunched into a small time duration, is known as the energy within that pulse duration divided by the pulsing time itself. So normally, as the standard unit of power is the watt, which is 1 joule emitted in 1 second or 1 joule conveyed in 1 second across a certain interface or something. Now, if you compress the same joule in 1 picosecond, that is, you emit this entire light, which is not so large actually, it's only 1 joule, but you crunch it into a time duration of 1 picosecond, which is 10 to the minus 12 seconds, you actually get a power which is called a terawatt. Because 1 joule divided by 10 to the minus 12 seconds will give you 10 to the plus 12 watts, which is a terawatt. Now, if you shrink it even further to 0.1 and so on, you get to 10 terawatt. You shrink it to 0.01 picoseconds, which is 10 femtoseconds, you actually get to 100 terawatt. So all you have done is to crunch the time or shrink the time in which you emit this energy. The energy may be the same, but the duration in which it's emitted becomes shorter and shorter, and the power of the light pulse actually goes higher and higher. The peak power, not the average power, but the peak power. And if you look at it now, if you look at extreme light as it's accepted right now, these are typically pulses of peak power ranging from 1 terawatt to 1 petawatt, and the pulse widths are typically sub-picosecond. 1 picosecond is 10 to the minus 12 seconds. So this is sub-picosecond. Usually 100 femtoseconds, hundreds of femtoseconds, or tens of femtoseconds. And at TIFR, we have had a system which emitted this much of energy in this duration for a long time now, for about 10 years. So that's a 100 terawatt laser. And if you focus this 100 terawatt beam with a focusing optic into a radius which is something like 10 microns, you can reach intensities which are 10 to the 19 watts per centimeter square. So at the moment it looks to you, so what? I mean, what's the meaning of 10 to the 19 watts per centimeter square? But it will all become very clear what this intensity means once I provide a comparative scale for you, right? So this is what I call extreme light. It's high in peak power, so extreme power, and it's extreme power which extremely short in duration. So time duration is extremely short, the power is extremely large, and that's what for this talk at least we define as extreme light. So this is how the laser technology has grown over the years. The laser was invented in 1960 by Theodore Neumann. In fact, in 2020, we celebrated the 60th year of the laser. In TIFR, we had a seminar. Unfortunately, that time I couldn't send you the link. We had a Zoom seminar, and we actually cut a cake for the laser. And of course, we ate it ourselves. And so Theodore Neumann's discovery on May 16th, I think, of 1960. So 60 years hence, the lasers have become monstrous. Their characteristics have changed dramatically. And if you see, soon after the laser was invented, people started making pulses of light, and they found out that they could make nanosecond pulses, or nanosecond is a billionth of a second. So they could make nanosecond pulses very nicely. And the nanosecond itself gave a lot of peak power because you shrunk the pulse duration to 10 to the minus 9 seconds. Now, that was stuck at the nanosecond level or gigawatt level. So 1 joule in 1 nanosecond is 1 gigawatt. So it was stuck at the gigawatt level for a long time, till a revolution happened in the mid-80s, and the peak power went up by a factor of 1,000, nearly. And after that, the slope changed, and you can see that the slope is now been climbing here inexorably. It's just marching on, more and more power. Today, we can get what is called a petawatt. A petawatt is 10 to the 15 watts. And, this picture is rather old, 2000, so 20 years before. But it took 20 more years for us to go from 1 petawatt to 10 petawatt. In fact, I'm very happy to tell you that this seminar is very appropriately timed. On the 17th of November, which was just last week, we had the unveiling of the most powerful laser in the world right now. It's a part of the extreme light infrastructure, which is an initiative of the European community, and this was unveiled on 17th November, as I said. And this laser can now produce pulses which are 20 femtoseconds and a peak power of 10 petawatt. 10 petawatt is 10 to the 16 watts, right? 10 to the 16 watts is huge amount of power. But as I said, the leaps are happening in many very interesting ways. And the next level would obviously be 100 petawatt, but we will see how long that will take. On the right-hand side bottom, you will see the picture of this gleaming new laser, which is located, as I said, near Bucharest in Romania. So there are 3 pillars of this extreme light infrastructure, one in Hungary, one in Czech Republic, and one in Romania. Each of them decided, with the goals of doing different things. This one is doing light-induced nuclear physics. You might find that very unusual that lasers can drive nuclear physics, but this laser will actually drive nuclear physics experiments in a very interesting way. And you can read all about it if you type out Eli-NP on Google. So you can try this after this talk. So this being a small step and this being a giant leap, and we are just now marching on bigger and bigger as time goes on. So this is the TIFR tabletop 150 terawatt laser that we have had for about 10 years now. These are all different quadrants of the laser. You see the green light which is bathing this entire picture. The green light is the laser that pumps the amplifiers. The real amplified light is of this color. It's from this crystal, a titanium doped sapphire crystal. that is emitting this orangish reddish glow, and a part of that at 800 nanometers is what is amplified as this 150 terawatt power pulse that comes out of the system. So we also have several other lasers. This is yet another laser which produces, may not be such high peak power, but still very useful, because the repetition rate of this laser, unlike the previous one was only 5 hertz, right? That means 5 pulses per second. This one is kilohertz, 1000 pulses per second. This is located in our campus, the new campus of the Tata Institute of Fundamental Research at Hyderabad, and where we are doing several interesting experiments on producing particles, charged particles and X-rays from this excited species that we use this laser with. And from there, we actually do a lot of imaging experiments and apart from fundamental physics. So this is located about 700 kilometers from Mumbai. And this is a picture we took with one of the Nobel laureates of 2018, who got this exactly for the invention of the chirp pulse amplification scheme, which made these tabletop terawatt lasers possible. So this is Gerard Moreau, who is a French physicist, and this is Donna Strickland, who is a Canadian physicist. Donna was the PhD student of Gerard Moreau when together they invented this system. That was in 85. And 33 years later, they hit the jackpot. They got the Nobel Prize. So we had the pleasure of his visit in 2009, and he also came back to India in 2014 for an international conference that we had hosted. And he's one of the big dreamers of this high intensity laser science. And Donna, as it turns out, is only the second woman physicist to actually get the Nobel Prize. And when she heard that, she was actually surprised. That's what I heard, that she was surprised that she thought that there should have been more people. So in fact, we hope that there'll be more women physicists who will work on experimental and theoretical physics and including other sciences. And so we look forward to them. And for our sake, I'm glad that we have one women physicist here, Saima Ahmad, who did projects with me during that time for 2-3 years. Now she has gone on to Europe to get a PhD, and now she is doing wonderfully as a postdoc. So this is me, and that's my colleague M. Krishnamurthy and other members of the lab. So this is how the wheel has been turning for intense lasers. About 15-20 years ago, there wouldn't have been a wheel at all. Now, this looks like a giant wheel that you see in several melas, probably in Bangladesh and also in India. And of course, in Europe, they are called, in London, if you go, it's called the London Eye. You can get into it, and then you can climb. When you go to the topmost, you can see the city of London. And that takes some time, actually go slowly. But I've seen whenever it's in a mela, it actually depends on how fast it has to go, depending on the adventurous nature of the people who climb on it. So this wheel has been turning and turning very fast, very beautifully. And you can see that most of the work, so this is all the locations of the intensity, high peak power lasers in the world. Europe is really the hub of this activity here. Lots of lasers in the US too, and in Canada. And the Asian continent has been doing rather well too, mainly because of China and Japan. And we have our own systems. We have, in fact, 3 lasers in India now. We have one ourselves. There's one at the Rajaramana Center for Advanced Technology in Indore, 250 terawatt laser systems. There's going to be one more in Bombay at the Baba Atomic Research Center, which is a 200 terawatt system. I think it's just being commissioned. And recently, we also have a petawatt laser at the Raja Ramanna Center for Advanced Technology Indore, in addition to the 150 terawatt. So that's a 1 petawatt, 0.1 hertz laser. So India, and to add to all of this, we will have a petawatt laser in Hyderabad. So you can see that, if you see, we have our Indian flag here, we have CAT, we have BRC, we have TIFR M, TIFR Mumbai, and also TIFR Hyderabad. So I'm sure and Bangladesh will join this very, very soon. And then we'll be happy to put a flag on, and a wheel, a spoke of the wheel pointing to that laser facility in your country. So, I've been talking about these laser can be focused to very high intensities. But what is high? As a physicist, you always ask, how high compared to what? How long compared to what? How thin compared to what? Right? How strong compared to what? So let's set a scale. And the scale is provided by matter itself. In fact, inside matter, as we know, there are Coulomb fields which hold the nucleus and the electrons together. If you take the hydrogen atom, that's a field of 10 to the 9 volts per centimeter. Convert that to intensity, it turns out to be 10 to the 16 watts per centimeter square. So 10 to the 16 watts per centimeter square, equivalent electric field is 10 to the 9 volts per centimeter. Now, today, already, even without the 10 petawatt laser, people have reached intensities of 10 to the 22 watts per centimeter square, which is a factor of a million larger than the Coulombic intensity inside matter, right? This is what is called 1 atomic unit of intensity. Now, this corresponds to 10 to the 12 volts per centimeter. Look at this. We can now have an electric field inside the laser pulse, which is 3 orders of magnitude larger, 1,000 times larger than the electric field inside the hydrogen atom experienced by the 1s electron due to the nucleus. So this is dramatic. In fact, till laser pulses of this monstrous intensities happened, there was really no way that an electron could be hit so hard by an electric field which is not the Coulombic electric field, right, of the nucleus. So now, if I ask you the question, which electric field should dominate? Obviously, the answer would be that this electric field should dominate the interaction or the behavior of this electron, and the nucleus will hardly have a role to play. It might just sort of be a weak link, weakly trying to hold this electron, which is very strongly driven by this 1,000 times larger electric field of the laser itself. So when you approach electric fields or intensities which are larger and larger, this is what happens. So normally in photoelectric effect, you're taught that if you have a level which is the continuum limit, and then you have a ground state of an atom, then unless you have an energy which reaches all the way from the ground state till the blue line, from the red to the blue line, you need one photon, and then only you can excite the electron into the continuum. Not so if you have an intense field. Even at modest intensities like 10 to the 13, 14 watts per centimeter square, you can have a ladder of photons, right? A ladder of photons being built up, so that in this case it's 1, 2, 3, 4, 5. The photon step itself is much larger, much smaller than the energy gap required for kicking the electron into the continuum. But nevertheless, 1, 2, 3, 4, 5 photons can gang up or can act cooperatively to actually kick the electron into the continuum. And this can happen even for much larger. You can have maybe a 10 photon process. You can have, n photon process, which is much larger than, where n is much larger than 1. So the Einsteinian photoelectric effect has to be modified as the multiphoton photoelectric effect, where the energy gap between the excited state and the ground state simply doesn't matter as long as you have a huge intensity, right? Because you build up this photon ladder. And if you increase the intensity further, go to 10 to the 16 watts per centimeter square, or 1 atomic unit of intensity, then another process comes in that was known as multiphoton photoelectric effect. Now you have what is called a different process, which is called tunneling. Now let's see how that comes about. So if you take a 1D model of an atom, so this is the potential of the electron, that binds the electron. It's given by minus q by x, right? So x is this coordinate of the electron from the nucleus. And now if you apply a very large electric field of a laser pulse, then the electric field of the laser pulse is a perturbation or is a disturbance plus minus E dot x. Plus minus because the electric field of the light keeps oscillating. So you have this plus minus E dot x, and you see it once again. So you actually have this thing called the seesaw that you must have played as a child, right? You must have sat on one end of the seesaw, your friend may have sat on the other end, and each of you trying to push the seesaw down. So the friend goes up, next time you go up, and so on and so forth. Now, while this potential, now the same thing is happening to this potential. This potential, which was stable and bound here, gets distorted by this external applied potential of the light, E dot x, and that makes the electron, that gives a possibility for the electron to tunnel out of this distorted barrier, and it's called tunneling or over the barrier annihilation. Now, the theory for this was actually done by Robert Oppenheimer. Beginning theory was done by Robert Oppenheimer in 1928 as a quantum mechanics problem. But in 1965, a Soviet physicist called Leonid Keldysh gave a wonderful exposition of this. He sort of made the theory much more robust, much more detailed. And this paper celebrated 50 years. There was a special issue of the journal JETP, or if I'm not wrong, the Uzbeki. Both are Russian journals now, which celebrated the 50 years of this very, very famous paper. So either by multiphoton or tunneling ionization, you actually will ionize any atom that is experiencing this kind of an intensity. And where is this intensity to be found? It is to be found at the focal point of a high peak power laser pulse. Now I'm very pleased to introduce, and I'm sure I thought of this, I should never forget to put this for this talk, and I'm glad I found this. This is Fahad Faisal, who is actually, I don't know where, which part of Bangladesh he comes from. I have forgotten, maybe Chittagong. I'm not sure, but he is a physicist from your country, and from the subcontinent, I'm proud to say, who has been at the Bielefeld University for a long time in Germany. And he has done some amazing work. He's a theorist who has done amazing stuff on multiphoton processes, strong field ionization, tunnel ionization, all these things. In fact, he even has a theory in his name. Is known as a KFR theory. The first time I heard KFR, it sounded like one of those acronyms, like. But then I realized that it is actually Keldysh, Faisal, and Rice. So Leonid Keldysh, I told you. Howard Rice is another physicist who did some of the work, and in between you have Farhad Faisal, who actually visited us. So I was very pleased to. I think he visited us in '95 or '96, and extremely intuitive physicist, very accomplished, and very, very kind. I was a young man at that time, and I asked him lots of things, must have annoyed him with my silly questions, but still he was so kind and he explained lots of things to me. And he showed interest in our work, which was just beginning at that time. So, very thankful to him for this. And do take a look at this book. So now the next thing, the light, of course, gets ionizes the electron, but the laser pulse could be much longer than the ionization time, right? The time needed to kick the electron out. So if the laser pulse is still there, what does the laser pulse do? The electric field of the laser pulse do to the electron? This is what it does. So let's click this. So the electron is sort of made to jump up and down by the electric field vector of the light, right, of the laser pulse, and the amplitude given by this laser light to this electron can be extraordinarily long. It can be as much as 10 to 100 nanometers. And compare this with the size of an atom. Well, I can't see you right now. Otherwise, I would have looked around the room and said, okay, what's the size of an atom? And I'm sure many of you would have just immediately given the answer, saying, no, it's about half an angstrom, Bohr radius, right? And half an angstrom, let's call it actually as 1 angstrom. That's actually 0.1 nanometer. This is, imagine, 100 to 1,000 times larger than that. So the electron can go far, far from where it was sitting inside the atom, and it is driven back and forth across across the nucleus in some sense. And the amplitude is given by this expression E by m omega square. The energy that is given in the oscillation is given by this expression, where this E square is I and lambda square is the wavelength square. So this is what is known as the I lambda square scaling, which is very popular in this subject. And so if you compute the electric field, take an intensity of 10 to the 19 for a lambda of 0.8 microns, which is a standard isophile laser wavelength, and an electric field which is corresponding to 10 to the 19 watts per centimeter square, you get about 10 to the 6 eV. Imagine 1 eV photon giving an energy of 1,000,000 times electron volt to the electron, right? The amplification is by a factor of 10 to the 6. Extremely unusual. It is not encountered in many, in fact, I don't know any other interaction in which the particle can transfer energy, which is 1,000,000 times the particle energy itself. It doesn't happen in charge particle collisions with matter. I don't know where it happens, but this is one place where it certainly does. So this is unusual. So everything is, so now one MeV electron is obviously relativistic electron, because the electron rest mass energy is half MeV, as you know, and acceleration that it takes to kick an electron from zero energy to 1 MeV in something like a picosecond or less corresponds to something like 10 to the 17 times gravity, which is abnormal, right? Extremely abnormal kind of situations. And so this is very, very unusual kind of interaction. Now, so if you now look at this, so let's look at the intensity scales. So you have 10 to the 13, 10 to the 14, where I told you that you have this nice way of putting out multiphoton excitation. Then you reach Coulombic intensity. Then you reach 5 into 10 to the 18 watts per centimeter square or so, or roughly of the order of 10 to the 18 watts per centimeter square. This is where the electron energy sort of matches its rest mass energy, which is zero point 0.5 MeV. And that's what is called the relativistic barrier. So you have a multiphoton regime, 10 to the 13, 14 watt per centimeter square. You have a Coulombic regime or super Coulombic regime beyond 10 to the 16. And then you have a relativistic relativistic threshold at 10 to the 18 watts per centimeter square. And above that, it's all relativistic interactions. Of what I mean is that it's called relativistic intensity, means that the electrons are driven to relativistic velocities. And if you go to 10 to the 24 watts per centimeter square, which we might do in the next decade or two, then we will be making even the protons relativistic, or the electron energy will go to 0 0.5 TeV. So imagine what we are doing. We are driving an accelerator, literally an accelerator with a laser. In fact, laser-driven accelerators are a great field by themselves now, an exploding frontier of intense laser interaction with matter. And the next generation accelerators, people hope, will be driven by lasers, but the interaction is not that of, it has to be a specified kind of interaction with a gas jet and so on and so forth. It's a very specialized field. You can read about it. It's called the laser wake field acceleration, or LWFA. So read about it and Google that, and you can find out the more literature on that. So now let's see what does an atom in an extreme light feel. So there's this monstrous pulse coming, ionize and oscillates it and so on. And the intensity is now touched 10 to the 20 watts per centimeter square. And everything here is going to be unusual, as you already saw from tunneling ionization. And now compare this with normal day-to-day optics as you walk out of your lecture room or your classroom in the university on a bright sunny day. And I'm sure the winter is very pleasant in Bangladesh right now, before it gets too cold. So experience the weather. And this is only about 1 watt per centimeter square. The normal light scales of interaction from sunlight and from lamps inside the room and so on, the atoms experience only at the level of 1 watt or a few watt per centimeter square. Now from 1 watt, we have gone to 10 to the 20. We're going to 10 to the 22, 10 to the 23. So imagine, and the only other number I know with 10 to the 23 is the Avogadro number, right? So now it looks like we have matched some kind of an Avogadro number, even with the light intensities. So it's very, very unusual and very, very far from normal optics that we experience in our daily lives. So that's a beautiful, yet, of course, optics is always beautiful. And this is a wonderful picture. I think it's from somewhere, I believe it may be the Himalayas or something, where this picture was taken. Beautiful picture of the rainbow, dispersion of light that you must have read in your school textbooks. And the interaction thing that I've been telling you about, people tell you that what are the principles that one should remember in any subject. In my opinion, this is something that you should think about even after you leave this lecture, that you have a photon energy which is 1.5 eV, which is 10 to the 0 eV roughly. The ionization energy of an atom typically is about 10 to the 1 to 10 to the 2 eV, which is much, much larger than 10 to the 0, right? But still you'll ionize atoms. That's the beauty of it, or the power of the light, laser light with ultra short pulses. And the oscillation energy that you give, the acceleration that you give to the electron, is much, 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 much larger than both the above. So it's certainly much larger than 10 to the 0 and 10 to the 2 eV. So this is something very unusual kind of interaction. And so this produces extreme states. The fact that it ionizes matter in such violent fashion, in such a small time, short time scale, and so efficiently leads to the creation of what is called high density coupled with. So simultaneous is written in capitals, simultaneous with, and that's extremely important because usually on the earth or in the lab, when you have high density, you have low temperature. When you have high temperature, you have low density. It's like if you heat water, it expands, it becomes gas, it becomes vapor, right? How do you keep water at the same density and still raise its temperature to extremely high values? So that's a challenge. But using laser pulses like this, you can produce high density coupled with, that is simultaneously with high temperature. So you have per unit volume a very, very high energy density. So the number of atoms each at a much higher temperature means that you have very, very high energy density. So how is the high energy density created by the ultrafast laser? The answer is very, very simple. The electrons are preferentially heated to millions of Kelvin so fast that the ions remain frozen in their positions. You know, all interactions of any particle with matter has to do with time scales. So there are things which move on very fast time scales. There are things which don't move on very fast time scales, usually given by their inertia. The electrons are much lighter than the protons and the nuclei. So their response time is of the order of femtoseconds, right? Ions respond on the time scales of picoseconds. So as you see in the next graph, or a couple of graphs later, uh, you'll find that if you shine visible light on a piece of metal or a piece of dielectric, the electrons are the ones that respond to this light. They take up the energy and they get excited within the short duration of the light pulse. And the ions are just remaining frozen where they are. And the density is basically provided by the ions, right, in a lattice. So that's the reason that these guys have high density. At the same time, the electrons are now extremely hot. So you have high energy density. So you look at a piece of solid. So you have this lattice, which I've shown on the left-hand side. Now let a light pulse come and shine on it. A very powerful light pulse. It ionizes. It makes the electrons jump up and down. As they jump up and down, they actually cause ionization, further ionization by colliding with the neighboring electrons in the neighboring atoms. And you can create a hot soup of these charged particles, ions and electrons, where the density is now, the energy density is contained in the free electrons, which are at 10 to the 23 particles per cc. So solids have 10 to the 23 particles per cc, but the solids are neutral, right? So here you can ionize 1 electron per atom, say, in that wherever the laser interacts. So you have 10 to the 23 free electrons per cc at a temperature which is 10 to 100 eV. Room temperature is 25 milli electron volts, right? That's 0.025 eV. So imagine how much larger this is. So this will correspond to millions of Kelvin. Room temperature is 300 Kelvin. This will correspond to millions of Kelvin. And the ions just did not move while this pulse was doing excitation. So you have this laser plasma interaction where on the rising edge, so this is a laser pulse that's given here. You have ionization, plus you have the collisional absorption that happens. And the collisional absorption will give you that, 10 to 100 EV temperature. Now the question is, all these things will happen on the rising edge itself. Lots of these things happen on the rising edge. If you take a 100 femtosecond pulse or a tenth of femtosecond pulse, there's a significant fraction of the pulse which is still there while all this is happening. So this rapid ionization and excitation by collisional absorption is what is called the pre-plasma that's formed on a solid target. And now what does the rest of the pulse do? So the rest of the pulse now starts exciting this plasma. And the plasma then it gets excited by what is called the collective modes. And I'll tell you a little about collective modes, which are very crucial for our work at TIFR. So let me just tell you what is this. So this is a pre-plasma. I have plotted density on the y-axis and x on the the position coordinate on the x-axis, which means that you have a solid on the right-hand side and an expanding plasma, because all these experiments are done in a vacuum chamber. So the hot gas that's being created on the surface of a solid freely expands, and as it expands, the density is sort of continuously varying as a function of the position coordinate. And this can be described by a dielectric function, which is well known. It's called the Drude model, where you have this omega p. Omega p is what is known as the Plassmann frequency. Omega is the applied frequency. Nu is the collision damping rate. So this omega p is a characteristic frequency of the plasma, which actually undergoes oscillations at a place called the critical layer. So when you have omega that matches omega p, this epsilon, if you ignore this I nu for now, this epsilon will actually become 0. And if omega p is larger than omega, this epsilon actually becomes negative. That means refractive index square becomes negative. That means refractive index becomes imaginary. So there's no propagation possible beyond that layer. So the layer at which omega is equal to omega p is called the critical density layer. And this side is called underdense layer, and that side is called the overdense layer. So light can penetrate only till the critical layer or the critical density layer of the plasma. So on this, I have just shown you a sketch of this. So if you have this light falling, and you have this blue target and this red plasma that's been created, the profile of which, the density profile of which I have actually drawn here. For lambda of 1 micron excitation wavelength in the infrared region, 1 micron, the critical density is about 10 to the 21. So this is 10 to the 21, this is sub 10 to the 21, and this is super 10 to the 21. So a lot of collective processes happen in this kind of a plasma. Various names are there. Let me give you a qualitative picture of what happens. So if you have one example of a collective mechanism is what is known as resonance absorption, which is very, very popular and famous. It's applied in many, many experiments. And this happens when an electric field, light is of a certain polarization. It's called a p-polarized light. That means that the electric field is in the plane of incidence. The plane of incidence defined by incident light, reflected light, and the normal. So the electric field is in this plane. And if you put the electric field component, vector component here, you notice that there'll be a component which is along the normal. The electric field has a component along the normal, so which is indicated here. And this component drives the electrons in the plasma back and forth across this solid interface, right? And that's how the wave are formed. And so this is the critical layer, and light actually reflects from there. And so at this critical layer, we can actually form oscillations of these electrons, which is called a plasmon or a plasma wave. So collective motion is what happens here. You have a powerful pulse. It comes, excites this, oscillations, and then goes out. So the waves form, they actually form and then they grow. So let me show you in one shot. So it excites this. Of course, part of this laser is absorbed in this excitation, and the reflected light then goes off as a smaller laser pulse, which leaves this. So the rest of the energy is actually dumped in the plasma. And when so much of energy is dumped, it releases what are called fast electrons. And these are the electrons which have much, much larger energy than the 10 to 100 eV that I mentioned. So the 10 to 100 eV that I mentioned is actually the bulk temperature of the plasma. These fast electrons can have energies which are billions of electron volts, not hundreds, but millions of electron volts, right? And we wrote a paper on this. You can read this for more details and ask me questions later. About how exactly this tsunami in a plasma. For India and Bangladesh, we have a huge coast, and we are familiar with cyclones and all the things that happen in the ocean. And the 2004 tsunami in the Indian Ocean created a lot of havoc in our region. So this is a tsunami in a plasma, but just replace the water with electrons. And just as a tsunami builds up to a huge amplitude and breaks, these electrons in a plasma also build up to a huge amplitude, and they can't be sustained, and they break. And when they break, they release huge amount of energy in the particles, which become these, MEV electron pulses, which propagate into the plasma. So this is actually a relay race between the light and the electrons. So let me show you. Light gets stopped here, releases electrons, which then go into the solid. So the excitation behind the critical layer or beyond the critical layer is actually done by these super fast electrons, which are created by this light pulse at the critical layer, right? So femtosecond light pulses produce femtosecond electron pulses, which then go inside the solid and create lots of excitation. So this is again something that you should carry home and think about, that if you have a dense target, the ionization of valence electrons happens by the light, no matter what its wavelength is. And then it also gives it a lot of energy by acceleration, the electrons. And then collisional absorption happens on a particle by particle scale. Collective absorption happens by this excitation of plasma waves and other coherent effects. And then finally, when both these things are dammed out, you have this hot dense plasma. So as I said, the crucial thing about all this is that the energy density is created, high energy density is created because the laser pulse is extremely fast. And so these are time scales. So the laser pulse duration is 10 to the minus 15 seconds, 1 frame per second. So this is 10 frame per seconds, this is 100 frame per seconds, 1000 frame per seconds, and so on. The laser pulse is in this duration, say, and the time scale of motions for ions is here. So the laser pulse is like a blip on the time scale of motion of these ions, which means that these heavy particles just don't even move. And that's the reason for this entire process. It's a recurring theme in ultra fast, ultra short pulse excitation of solids. That the light pulse is much, much faster than the response time of the ions. So this is an area which is called laboratory astrophysics. So literally the heavens coming down. You can create them on a tabletop because you can create huge charge densities, free charges at the level of even 10 electrons per atom, like in some systems. So 10 to the 24 particles per cc. And then these electrons are highly energetic, so 10 to the 3 to 10 to the 6 eV. And similarly, you can have extremely large physical parameters. Magnetic fields can be billions of Gauss, that is 1 billion times larger than, or 10 billion times larger than that of the Earth. Pressures which are 1 gigabar, which is again a billion times larger than the pressure that which we all live on the Earth. Temperatures again close to a billion Kelvin and so on. So this is a thing which is normally not encountered in a lab on the Earth, but it's a part of the universe. It's the dominant part of the universe that we see. Stars are full of these conditions. Stars are not full of low temperatures, moderate pressures, nice weather, right? Everything that sustains life on Earth. You look above and see the stars in the sky tonight, and you will see that these are the characteristics that they have. But you can also think about going deep into the Earth or deep into a planet, and there again, you have very high temperatures, high excitation, and because of all the layers that are compressing the inside, so the densities at the core are also much, much higher. So you have either above the Earth surface or deep below the Earth surface. You have these kind of conditions. But how do you create them in the lab? Well, you need to have an ultra fast, high intensity laser. And of course, this field is exploding because it unites all of physics in one tabletop. You can do nuclear physics, atomic physics, plasma physics, astrophysics, even particle physics experiments in the near future on a tabletop in your lab. You don't need to go to accelerators, right? Which is what is the greatest thing about these kind of experiments. So let me show you the density scales. This is lots of things in the universe. You recognize the solar core, white dwarf, Jupiter core. What do I have on the right, on the y-x-axis? The number density, charge particles per meter cube, not cc but meter cube. On the y-axis, I have a temperature in Kelvin. These are all log scales. So you can see that the solar core is at something like 10 to the 29 or so of particles per meter cube, but a temperature of something like 10 to the 7 Kelvin. And you can see the initial confinement fusion, or laser fusion as it's called, is quite there. It's already quite there. The densities are quite large, temperatures are similar. So this is where we hope to release energy by fusion, laser fusion for mankind, and save this Earth from the bad effects of the carbon pollution that we are creating by other means. So lots of things here which are all captured on this, but this is the kind of excitation that we can do with laser light. So I wrote a short tutorial review way back 11 years ago. I believe it's still useful because it's a tutorial. So do take a look and tell me if how you would like to write it differently, what else you would like to have. Perhaps it's time for a revisit of this review article. And I'll thank you for your comments when I rewrite this. So how is the laser energy shared in the plasma? So there are electrons which are up to 100 eV, the hot electrons which are up to keV to meV, and femtosecond light pulses can produce femtosecond electron pulses and so on. And the scene of the action, when you have a light pulse hitting a target, looks like this. It's explosive. It's explosive because the light pulse comes instantaneously within a few tens of femtoseconds, shatters the solid, ionizes it, accelerates the electrons. The electrons then start interacting with the rest of the solid, and all kinds of exotic, extreme physics happens. You can have relativistic electrons, as I showed you, and these relativistic electrons can lose their energy by X-rays, gamma rays, terahertz emission. Then they can also transfer energy in different ways to protons at the back of the surface or the front of the surface. And you can produce ions, you can produce visible light pulses, you can do amazing things. And these electrons can also go into the solid at extremely large velocities, and when they go there, they actually create the current densities of the order of terampere per centimeter square. Take a moment to appreciate this. Trillion amperes per centimeter square, right? 1,000 billion amperes per centimeter square, which is unusual, right? I don't think any other situation exists like this. And these produce extremely large magnetic fields. One of the major themes of the TIFR group has been looking at these kind of magnetic fields. So let me come there. So this is a one-stop, one tabletop for all kinds of physics happening here, right? And very exciting stuff. So obviously it's a hot, dense, violent, turbulent, very rapidly evolving environment. And for an experimentalist, it's a challenge because so many signals are coming, and your signals have to be measured independent of other signals which can mask it, which can interfere with it, or which can actually sometimes damage even the detectors. So it's a big challenge that we face in the lab on a day-to-day basis, but we are learning to overcome all these things. So the collective absorption process, as I said, carries away huge amount of energy, about 40% or so. And this forms the femtosecond current pulses, which are of the order of mega amperes. So in normal day-to-day life, you only have amperes of current. I don't think you think of mega ampere currents, but these are mega ampere femtosecond current pulses. So how do you see these electrons? The fact that these currents are actually there is by doing what is called taking picture snapshots of these relativistic electrons. And this is what is called, literally it's a taking a picture. It's like, all of us have become used to taking selfies and uploading everything that we do in our day-to-day lives in the social media age. So this is not a selfie, but somebody from outside taking a picture of these electrons. And so if you can see here, somebody hits with a laser, these electrons are going in the form of a jet here, and somebody has taken a snapshot from the side at a time of 1.2 picoseconds after the laser pulse has hit it. So from this distance, from the time, you can calculate the velocity, which turns out to be 0.6, 0.7 times the speed of light. And you can see this cloud here. This cloud is formed by the ionization caused by these relativistic electrons which are streaming in. They ionize other electrons, they create a dense hot soup. So if you send light from the side, the light is actually blocked by this overdense plasma. It doesn't allow it to pass through. So you see what is called a shadow effect. And apart from the semi-isotropic cloud, you have these two jets which are going like one of those fighter jets that you have in the Air Force. Typically you have this, they go at ultra large speeds on our scale, and they go at, they cross the sound barrier and so on. These ones are going very close to the speed of light. So these electrons going at the speed of light, nearly the speed of light in this system. So this is dramatic. So, but then the question is, all right to take pictures like this, but how do you measure the energies of these electrons and lifetimes? For example, how long do they live inside the solid? That's a very good question to ask. That tells you how rapidly they're dumping their energy into the solid. So imagine, now you can get some idea of the energy from here. The velocity of these electrons. You can take the relativistic electron energy expression, and from there you can compute the energy of these electrons. It'll be some MeV, right? But that's not the same thing as actually measuring the electron energies directly. So there's a nice way of doing that, which is what is called Cherenkov radiation, which has been used, discovered in 1939 by Cherenkov, Pavel Cherenkov, and he was given a Nobel Prize in 58 for that. And particle physicists have used it for the last 50, 60 years to look at cosmic particles or particles in accelerators and so on for a long time. And so the idea is very simple. If a particle moves in a medium faster than the speed of light in that medium, then this radiation is emitted, which is called the Cherenkov radiation. So the principle is a particle moves faster than light inside a medium. Inside a medium, the light slows down by what is called the refractive index, right? So inside any glass piece, for example, light travels at c by n, but an electron can be going faster than c by n, right? And if that is the case, then the Cherenkov radiation is emitted in the form of cones of light, and the cone angle is decided by how fast the particle is. The details are all given here, or you can read our papers. I'll give references to in a short while. But this is a wonderful technique to use. So you can make these measurements, and we did that in a measurement long ago. One of our first studies in collaboration with Japanese visitors in our lab, a joint experiment where we use pulses 30 femtoseconds, 10 to the 19 watts per centimeter square. We hit a target, and then we saw Cherenkov radiation. Because of the peculiarities of the geometry of this target, it looks like a horseshoe nail, right? And then this is the spectrum of the electrons that you can get. You have energy on the x-axis and number of electrons on the y-axis. Different measurements. So these are our measurements. So these are our measurements. These are simulation, and we very closely match simulation. Other measurements which were done outside the target do not reproduce this thing at all. So we used very carefully the title, the words here. It's a direct measurement because we're measuring emissions from particles inside, not particles that have left the target and come outside. It's absolute because we can see the correlation between the number of particles here and the amount of light that comes out. And it's in situ, inside the glass itself, not outside the glass. So we did something more recently, which was published 2018 by my graduate student. This was his major part of his thesis, Moniruzzaman Sheikh, who is now in the US on a postdoc, and in collaboration with French physicists and so on. So we have here, we wanted to know how fast these electron pulses lose their energy. So we use the same technique, but I'll show you how we measure this. But we use the same technique to measure their lifetimes, to measure the fact that they emit Cherenkov radiation. So, but the question that some of you must be thinking, oh my God, these guys are happening so fast. These things are happening so fast, femtosecond, picosecond. How do you see them? There's no camera that can click this fast, right? Cameras don't click on picosecond and femtosecond timescales unless you design them specially. So how do we design such a camera? So that's what we've been doing for decades at TIFR. In fact, this is one of our strong points, that we look at ultrafast dynamics by using what is called pump probe studies. And the pump probe study experiment looks like this. So there's a pump pulse which comes and excites the target, creates a plasma. Then there's an independent pulse which is timed with this, which is related to this, but independent, meaning you can define its time with respect to this pump, right? But you can change it's an independent pulse, so you can control its wavelength, you can control its polarization, you can control whatever you want. You can code information in this that you want to send it to this target and retrieve that information after modification. So this pump goes excite, the probe goes and feeds what is the state of the system at a certain delay after the pump, and then we actually get this, we can get information. And so you can see all our previous work here, which is mentioned. So this is how we do our experiments here. So we do all of them in a vacuum chamber. A pump pulse comes, hits the target. A little later, a probe pulse comes and then gets reflected, goes to various detectors, which then display a characteristic signal. So you can measure the spectrum, you can measure the reflectivity, you can measure the polarization and what have you. So this is how these experiments are done. This is inside our vacuum chamber. All these things have been built by PhD students. So you should enthuse yourself that these are not difficult to do at all. These are not difficult to learn. If you're enthusiastic about doing experiments, you can do all these things yourself. So that's a very good lesson to take home. So there's a pump pulse that I've just showed you. So the pump pulse comes like that through various optics, goes and creates a plasma. Then comes the probe pulse a little later that I have not shown, and then that actually probes this inside. So let me show you, I just hinted at what we do. So we time these electrons, we measure the lifetime of these electrons inside a solid. by gating this Cherenkov emission. The details are a little complicated, but we use the same Cherenkov emission, and we use a nonlinear optical effect called the Kerr effect, and we time these electrons inside how fast do they live. So you basically have this target which has emitted, like for example, there's a Cherenkov emission has been captured from a target which has been hit by a pump pulse, travels all along this direction, comes to a Kerr gate or optical Kerr effect cell, and where you have this gate opens only when this pump laser comes in here. So there's a timing of all these pulses is extremely crucial, and so this is a gate that opens and closes as long as the pulse is, this red pulse is alive here. So you can gate this pulse and you can measure various things. And this is how we measured out the lifetime of these electrons, or the lifetime of the Cherenkov emission. And we were surprised. For example, this is a laser pulse, right? And this time is the delay through all the optical components through which the Cherenkov emission travels. And you notice that this emission is much, much longer lived than the input pulse itself. It is expected to be, but nobody thought that this would live as long as hundreds of picoseconds or tens of picoseconds. They thought it would die very, very soon. But that means that the electrons are so high in energy that takes such a long time to dump their energy inside the glass lattice, right? We did this in several targets. This is a BK7 glass. This is LASF glass. Refractive index here is 1.5. Here the threshold for Cherenkov emission is 174 keV. Here the threshold for Cherenkov emission is 79 keV, and so on. So this is the experiment that we did, and we tried to do some theory for it. The theory is not yet fully satisfactory. And this is what we published 2 years ago. You can read the details about how this excitation is dumped inside the target and what kind of excitation, what kind of further excitation that does inside the glass piece. So this is, again, as I said, this is a favorite, and maybe I'll use this as a last example to conclude my talk. So, they produce, I said megaampere currents produce mega-Gauss magnetic fields, and these mega-Gauss magnetic fields don't exist routinely on the Earth. In fact, they exist only in the stars. And so maybe you can do some astrophysics kind of experiments right on a tabletop in your lab. So this is the first current pulse that we measured. The technique is what is called something similar to Faraday rotation of the probe beam that goes into the plasma that's excited by the pump pulse. The details I'm not presenting here in view of shortage of time, but you're welcome to send me questions, or we can have separate discussions later on Skype or on any other internet forum. So this is the pulse that we measured out in 2001. In fact, this was Ravindra Sandhu's thesis. He's now, as I said, is a professor at the University of Arizona. And this was a surprise because we found out the laser pulse is somewhere here. It's actually 30 femtoseconds or 100 femtoseconds. 100 femtosecond, the pulse grows much, much later and decays, and the duration of the pulse itself is something like 6 picoseconds or so, 5 to 10 picoseconds. So we did more measurements recently. We produced, that was 30 megagauss, right? This is 65, 70 megagauss, lasting again picoseconds. And physics is all captured here. So just a quick undergraduate physics explanation is this, that you have this laser which hits it here. It releases hot electrons, currents, which go inside here. These relativistic electrons go inside here. And the electrons, if you take this to be a metal, electrons cannot, the current cannot sustain itself inside a metal, because the metal will try to reduce the electric field by launching reverse currents or induction current. So these are the green, the ones that are shown by green curvy arrows are the return currents. And so these currents try to nullify this forward current, and the magnetic field lasts as long as this forward current is not nullified by the return current. So the expression here is this is the source term, and then there's a diffusion term, and the crucial thing is conductivity here, and the conductivity controls how fast these electrons, these return currents, are set up inside the system. So if we also measure out this magnetic field, the spatial extent of the magnetic field, and literally it looks like this. So what I'm showing you, let me pause here and play this again. So what I'm showing you here is the 2D evolution of this magnetic field inside the plasma. And I'm showing a time clock here, which, as you see now, this is the 2D part, So the transverse area of the plasma, which is being shown here. So different parts of the face of the plasma, and then you have a clock running here. You see clock running and the magnetic field spiking at different places, and highly inhomogeneous, highly sort of spotted, full of peaks and nulls like that. So very unusual. And again, the magnetic fields are of the order of hundreds of megagauss. So this is what is known as filamentation of these currents on the magnetic fields. So these are computer simulations done way back in 2002. So if you see here, A and B are the magnetic fields of such a current launched at the left end of this plasma box. And so they filament, they become segregated, they sort of filament themselves. And there's electron density shown in red here, which again shows breakup of this electron beam. So why does the beam break up? When the fast electron currents and the cold return currents are going opposite each other, this is like two wires conveying one current in one direction and a current in a opposite direction. And you know what happens to two wires which are carrying currents in opposite directions? What do? They interact with each other. In fact, they repel each other. So exactly the same way, these guys also repel each other, and then they sort of break up due to what is called a Weibel instability. And the Weibel instability breakup then causes the electron beams to break up into filaments, and the magnetic field is then produced as an inhomogeneous, localized, filamented, fragmented magnetic field, right? And we were one of the first people to show this kind of filamentation in a system. So there's a beautiful map of the filamentation of the magnetic field, a spotty picture of the magnetic field across time on a two-dimensional scale. But if you take its Fourier transform of any of these pictures, normally they look very random. They look very random, uncorrelated to one another. But if you take Fourier transform, they all form beautifully on these curves here. This y-axis is the log of the magnetic energy density. X-axis is the log of the 1 by x, which is the inverse of length scale. And you notice that all of them for different pictures, you get the Fourier transform. It all follows the slope of -2. So this is what is called a power law with a slope of -2. And this indicates turbulent magnetic field that has been created in the plasma. So this is what is seen in the sun, right? And this paper was published in 2012 and a story was written on this. And this is the turbulent magnetic field. You must have seen pictures of this. In fact, there's an Indian astrophysicist, Arnav Rai Chaudhary. I don't know if you have heard the name. He's very famous for his solar magnetohydrodynamic studies and predicting of the sunspot activity, the sunspot cycle, and so on. And he's at the Indian Institute of Science, Bangalore, and he's written wonderful books on plasmas and fluids. Please do take a look. And also a book on what is called Astrophysics for Physicists. Wonderful. He's a great writer and very knowledgeable on this field. So these are the pictures that I first saw when he was giving one of his talks. And then later I captured lots of them on the internet. So this is how the magnetic fields look. We did more and more studies and we found out that this kind of power law behavior, mimicking very much the kind of systems that we see. For example, we see this kind of power law spectrum, and pretty much the same thing is seen in the solar flare loop, solar photosphere, and so on and so forth. So we wrote a paper saying magnetic turbulence and a tabletop laser plasma relevant to astrophysical scenarios, right? So this also merited a sort of a comment in Nature Physics called turbulent tabletops, and they said they called it a miniaturized solar system in the lab. So that's proof enough that people are willing to believe this, that such things can be created. So I want to just conclude in the next few minutes, maybe a couple of minutes, by saying that the lasers can not only produce charged particles like ions and electrons, but they can also produce neutral beams. This is a study done by my colleague M. Krishnamurthy and his students completely at TIFR, where they made a neutral atom accelerator, where they ionized a piece of matter and gave it a huge amount of energy to the ions. And while the ions were exiting the plasma, they transferred electrons back into the charged ion in some sort of fashion. And so the ion had energy, but then it was neutralized, right? So this is one of the fabulous ways of producing neutral atoms. Otherwise, you know that neutral atoms cannot be accelerated by electric fields. So this does a two-step process. It ionizes the plasma. It ionizes the target. The ions are now hot, sort of, because they've been excited. They're exploding, and as they move out of the plasma, they get neutralized by the electrons which are in the neighborhood, and then they produce these neutral beams. So this is a global first. And recently, our lab has also produced, M. Krishnamurthy and colleagues have also produced protons, neutral hydrogen atoms from a solid target. That earlier one was an argon gaseous cluster target. Now they can do it with literally any target. They can produce neutral atoms. So, in short, these have been our themes over the last couple of decades or so. So we are excited about the basic physics of this interaction, how to make this interaction better, how to control this interaction, how to study the extreme level of shocks that are created in this, right? The acoustic waves that are launched, how do we excite neutral atoms, and to top it all, we also feel that this is a wonderful source of terahertz radiation, and terahertz radiation is one of those hot topics in physics and technology these days, right? So where are we going? So this is where we are. I am really literally on the west coast of Mumbai, next to the sea. In fact, I can see the sea as I am talking. And Professor Das was here 2 years ago, 3 years ago, and he would vouch for this, that we can walk to the sea in just a few minutes from here. And so we have a 150 terawatt, 20 terawatt systems here, two systems. In Hyderabad at the moment, we have a kilohertz system, but we are acquiring a 1 petawatt laser system. So Indore, that I mentioned, is somewhere in the center close to Bhopal here, and BRC is Bhabha Atomic Research Center. So in Bombay, there'll be two high intensity lasers of the femtosecond variety. Indore has two of its own, and Hyderabad will have two of its own very soon. So we want to go to 10 to the 20 and so on and so forth. We want to do extremely exotic physics. Lots of topics listed here, and we hope that some of you will come to our country and join this research. Let's hope that this will happen and we collaborate more and more. And the world is racing away to higher and higher intensities, higher power, peak powers. So we have called what is called the atomic era. We have left behind already. We have a plasma era at the petawatt level, petawatt per centimeter square to 10 to the 18. Now we are going into the positron electron era, and then we might go into the quark era and the electroweak era as you go to above 10 to the 25 watts per centimeter square. So what do we want to do? We want to do all of physics at Hyderabad. So we'll have a petawatt laser, we'll hit a target, and we'll do astrophysics, accelerator physics, warm condensed matter, and particle physics, right? So lots of things on the table. And let's hope that some of these things will become realities in the near future. We also have an Extreme Photonics Innovation Center at TIFR Hyderabad, mainly to focus on the spin-offs of the laser excitation, which are all these particle sources: high energy electrons, high energy X-rays, high energy gamma rays, high energy ions, right? These calls can be used for imaging various systems in condensed matter and biology, for example, cancerous tissues and so on and so forth. So we have started an innovation center in collaboration with UK. And this is where I'd like to conclude saying that this is an extremely exciting area of research. All of it boils down to the hot electron currents that you can generate inside a piece of solid. And this high energy density science it's a wonderful field which should see convergence of many, many scientific areas on a tabletop. And so thank you, Dhanyabad, and thanks for all your patience. And once again, to Pretam for his persistence and his enthusiasm for organizing this webinar. Thank you very much.
Thank you, sir, for your wonderful presentation, sir. So I think students have learned a lot of things about the laser physics and plasma also. So if you allow, we can start our discussion session. So we have got some question in inbox and the comments. So
sure.
If you allow,
Will I be able to see people now? Because I've been seeing the screen.
Yeah, you can see the comment after stop the share. You can see the
Okay, I stopped the sharing, but maybe I need it for. Well, I'll minimize this and see what I can do.
Yeah,
Do I see? So
come
I should
inside the
stop sharing.
SteamYard.
Okay.
Yes, and come the SteamYard screen so that you can see the comment of other.
Okay. Okay. Yeah. Yeah. I had pushed it to the side, so I stopped
Yeah.
sharing. Is that okay?
So can
Okay.
you?
So where am I now? I don't know where I am. I think I am
So
somewhere here.
yeah,
Good. There I am. I'm glad to see. In fact, I didn't know who I was talking to. I hope there were still people on the in the audience.
yeah, there are few. So the first question in the inbox. So I think the so what will happen when the laser light interact with plasma matter?
Well, it causes excitation. In fact, my whole talk has been on the excitation by this laser system. So, the light is taken up by the particles in the plasma, mainly the electrons, right? So the
Yeah.
electrons get kicked up. I said there are collective waves. There are these oscillations which then grow to a large amplitude and then break like a tsunami. And once the tsunami is there, tsunami is broken, it releases lots of energy into the particles and so on, generates fast electron currents, which are then the story of the subsequent evolution, right? So, in short, the answer is that it excites the particles very, very strongly, and you can create all sorts of abnormal situations like high temperatures, high magnetic fields, high pressures, and all that stuff.
Thank you, sir. We have another question in the inbox. So what is the dense hot soup? Maybe you have
Okay, the
explained.
dense hot soup. Well, is it close to dinner time in Bangladesh? Not yet.
Not yet.
Okay, I know that. Well, Bengalis love to eat late at
Yeah.
night.
Yeah.
So, well, maybe this is your snack time and the
Yeah.
the adna time probably.
Yeah.
Okay, so I called it a soup because it's a hot gas of particles, right? It's a you call it a gas, but it can be extremely dense. So I called it a soup because it's actually called a plasma, which is ionized electrons and residual ions, which are all existing together, right? So that's what I call a soup. You can also call it something else that you like, your favorite name for it. But it's a hot, dense volume, it's a volume which contains this hot, dense matter, gas, solid, and some of it can be. Sometimes you can actually reach densities, and some of the laser experiments you can compress. Normal density is 10 to the 23 per cc, but you can compress the matter by laser pulses to a factor of 10, a factor of 100 larger than this. So, which is just truly spectacular. That means you have high density and then you have this. In fact, that's how the laser fusion is supposed to work, actually.
Thank you, sir. So we have
Yeah.
a question in comments. So can you give some ideas over the soft X-ray laser, so which is very famous in attosecond science?
Okay. So that's, intense lasers have done several things. For example, intense lasers can produce radiation of all types from visible light all the way to gamma rays, I said, right? Now, in fact, the Eli petawatt laser that I mentioned, which has just been commissioned on 17th November, will produce gamma ray beams, right? At a high flux, but shots, 1 pulse per minute, but very high brightness gamma ray beam. On the other hand, they can also drive, just as we were driving coherent oscillations of these electrons, we were forming waves of them inside the plasma. You can drive similar waves in matter, right? Either in neutral atoms or even in plasmas like this, where you can set up these oscillations of electrons, and that can then re-radiate coherent radiation, which is what is known as the high harmonic. For example, ever since lasers were invented, people knew second harmonic, third harmonic, and so on. And but now you can go to something like 1,000 first harmonic, right? Or a 2000 first harmonic. What does it mean? If you take one EV photon, you're going to 2 keV, right? 2000 EV. And all these radiations they happen on attosecond time scale. It's by the nature of the process itself that they are actually attosecond. And they're soft X-ray or hard X-ray, depending on which harmonic you're looking at. And the beauty is that this is a coherent radiation. This is a coherent laser, X-ray laser. There is no other way of making a coherent X-ray laser. You can make X-ray lasers from a glass plasma discharge, from a gas plasma discharge, but for a laser you have to put mirrors to produce feedback and make a laser to induce coherence by feedback. But that is very difficult as you go to higher and higher X-ray energies. But you begin with a 1 eV coherent source, and you can produce a 1 keV coherent source. So truly coherent X-ray pulses can be produced like this, which is amazing.
Thank you, sir. We have another question. So wonderful physics, but how this work really benefit our daily life?
Oh my. Okay. It benefits the human mind, and the human mind can then think of lots of applications. But in this case, applications are, you can always see tabletop accelerators, right? Tabletop gamma ray source, which can kill a cancer, which can kill a tumor. Tabletop electrons, very fast electrons, which can kill a tumor or which can image some cell inside a body, right? In fact, these kind of laser produced protons have been used they're proposed to be used in Europe. There are big projects which are funded by for medical applications, where these protons will go and kill cancerous cells. The protons you need some tens of MeV, 100 MeV or something like that. And if you can produce them, you can actually kill selectively the tumor cells without damaging the neighborhood. And so people are very excited for imaging, for material modification. You can take this electron pulses as, for machining very precisely, right? And you can have stars in your lab. You wouldn't like to have stars in your lab?
Yeah, that will be very amazing thing. So thanks, sir, for your wonderful presentation and exciting discussion session, sir. We'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. It was a great webinar with you, sir. Our students have benefited lots about, and they maybe learned a lot of things about this field. So this is an exciting field, and so in the near future, we have to go this field to develop tabletop laser and exciting tabletop accelerator also using the laser. So that will be very exciting for the new generation physicists. So thanks again, sir. And I will definitely send you our 100th century the webinar with the Nobel laureate. So it will be very pleasure for me if you will present with us, sir. So thanks again.
Well,
sir.
I can't resist saying that David Weinland's stack will be in the other extreme. He will be talking about, I think, very low temperatures.
Yeah.
So
yeah,
it is a good thing that 95 you have. Now you hit a sixer and you go to 101, like Virendra Sehwag used to do in cricket.
Yeah.
And so thank you once again, and please do ask me more questions.
Yeah.
And we are neighbors, so we can
of course,
exchange.
and we'll discuss. And I think we can discuss more about the probation work and short-term research project and something like that in future.
Absolutely,
so
absolutely.
I'll definitely email to you, and maybe some of my students also fall in love in this field, so they might email to you. So
I do hope that they will. But towards the end, maybe I got too technical, in which case I apologize. But I hope you got the first half of the talk, and that should excite you to probe more. And you can also go to our website, and you can download all our papers from there, right? So it's a free source of information. And do discuss not only with me, but members of the other group who are listed on the website. So thank you very much, and dhanyavad once again.
Yeah, dhanyavad, sir. Thank you. It's my pleasure and honor to host you in our international physics webinar.
Thank you. Thank you very much.
Yeah, good night, sir. Bye for today.
Bye, Pretam.